Now, let's try to understand what histogram of oriented gradients are. And by the name, you can guess that, of course, this is a histogram, and you know what a histogram is. And of course, you are going to use images to create these histograms. And if you just go through these terms you have in the name, it's saying like oriented, right? And orientation, you know, is like the direction of your edges, and it's talking about gradients. So in a way, you can guess that what you're going to do is, given an image, you're going to find edges, and those edges or those gradients, you will also take the orientation into account, and you are going to create histograms using those gradients. And that's exactly what this algorithm does. Okay, so let's quickly go through like each step we have, and then we'll talk about each step like in more detail. The first step is, given an input image, you will have like for each pixel location, you will have some pixel value, right? So whichever pixel you choose, it will have, if it's an RGB image, it will have 3 different values, right? So what we want to do is, for each of the such locations, we want to create HOG feature for that pixel. All right, which means that we can actually compute HOG features for all the pixel values. Okay, so basically we have 5 different steps how we can do it for each pixel. So we'll first do for one pixel, and then you can just repeat that for all the pixel locations to get features for the whole image. Okay, so let's try to understand how we can extract for this location. So what we do is, we first again draw this block here. And again, so far you have seen like we use a lot of these blocks, right, when we process images. So you will see like these are throughout the course. So what you do is, you draw some kind of bounding box. You can call this a block as well. So this is like a square window. And again, I mean, this was something which was proposed. It should be a square window, but usually you can have like a odd shaped window as well. So it's not like kind of a restriction, but the standard algorithm uses like a square window. So then what you do is, you divide that block into, again, multiple cells. And in this case, we are dividing into 4 different cells. And of course, you can divide into more than that as well. But let's like go through once, and then we'll see like how that affects the final algorithm, like how many cells we are actually dividing this block into. Okay, so first step was drawing the block. Second step was, we divide that block into multiple cells. In this case, it's 2 cross 2. Okay, so this blue region is called block. So try to understand the terminology as well, because we'll use that a lot. The blue block, the blue square is the block, and these smaller ones are cells. Okay, so we have 1 block, and we have 4 cells here. So this is like a 2 cross 2 grid. Okay, now what we do is, for each cell inside this block, we simply compute a orientation histogram. And we'll talk about what orientation histogram is. But you do that for each cell. You will do for this first cell, second cell, third cell, fourth cell independently. Okay, and you just concatenate those histograms together. So you know that histogram is nothing. It's, let's say if you have 10 different bins, so histogram is going to be 10 different numbers, if you think about this, right? Because for each bin, you will have some value. And at the end, if you have to describe that histogram, it's just 10 different values. So in this case, for example, if you are extracting a histogram which has 10 different bins, this cell will have 10 values. Again, this will have 10 values, and same for these two. And you just concatenate those. So at the end, for this whole block, you are going to get 40 different values. Okay, you just concatenate those. And those 40 different values are actually your features for this pixel location. Okay, now the only missing link is, how do we extract this orientation histogram for each cell? All right, so we will come to that. Now, once you have this 40-dimensional feature for this whole block, we perform some kind of normalization. So you can represent that as a vector V. All right, when we combine, like, let's say all 4 histograms. So we try to normalize this. And again, normalization, you know what normalization is, and there are different ways to normalize, and it's up to you, like which technique you want to use. The whole idea is, you don't want like numbers very big and very small. Okay, so one simple way is you can just divide like all the values in your vector with the Euclidean norm. Okay, so that's one way. You know what Euclidean norm is. So we don't have to discuss a lot about that. The other way could be you can divide with, let's say, L1 norm. Okay, and again, you know what L1 norm is. So there are different techniques for normalization. And as I said, you can use any of those. And the third option is, and we are discussing these three because the actual work which proposed this, they tried to do ablations on these three variations. Okay, so some of these, one of this is better, one of this is bad. So, but again, we don't have to worry about it. Just try to understand that it's a normalization step. Okay, so the third option, it was a little more complicated. And the intuition was okay, so let me go through the steps first. So first you divide by Euclidean norm, which was like the first option you had. And then what they try to do is, if any value in that vector is greater than 0.2, they will just clip it to 0.2. Okay. So then the idea is, even after normalization, you are performing a second step of normalization. And this is required because you might have some kind of outliers. Okay, if some value is actually too big. So even if you normalize, then still that magnitude will be there, right? So to take care of those outliers, what you do is, if some value is too big, you just clip it. When you don't care if it's 0.3, if it's 0.5, if it's 0.8, you bring all them down to 0.2. Okay, so it's kind of, you can say you're discretizing your values. And once you did that, then you again renormalize. You can just compute Euclidean norm and divide. So it's like a second step. And again, it's just trying to take care of outliers.